Welcome to The Explainer. Okay, let's just jump right into it today, because we are tracking down one of the absolute most mind-bending theoretical concepts in all of astrophysics. I mean, we're all pretty familiar with the usual cosmic heavyweights, right? You've got ordinary stars burning nuclear fuel. You've got ultra-dense neutron stars and, of course, light-trapping black holes. But what if I told you that our universe might actually be populated by massive, completely invisible structures that totally defy every traditional rule of stellar physics we have? We are literally talking about macroscopic quantum objects just hiding in the dark.
So I really want you to hold on to this provocative question as we go. Could invisible stars, made entirely of exotic quantum particles, be hiding throughout the universe? And even crazier, could they be masquerading as the very black holes we think we've already discovered? This is the ultimate cosmic mystery. It's a true detective story, where our suspects are completely invisible, and the clues, well, they're written into the fabric of space-time itself.
All right, here's our roadmap for the explainer today. We're going to cover 1. The invisible star mystery. 2. What exactly is a boson? 3. Define gravitational collapse. 4. The dark matter connection. 5. Cosmic impostures. And 6. Hunting for phantom stars.
Part 1. The invisible star mystery.
Now, you might be thinking, this is just some trendy new theory, but it actually goes all the way back to 1955. Legendary physicist John Wheeler envisioned these smooth, self-gravitating bundles of electromagnetic energy, and he called them geons. The only problem, they turned out to be mathematically unstable. Fast forward to 1968, and a team, Kaup, Ruffini, and Bonazzola, they basically cracked the code. By swapping out electromagnetic energy for a massive scalar field, they found stable, localized, non-singular solutions. They dubbed them Boson Stars. And today, this concept has evolved from a quirky mathematical oddity into a prime suspect in modern multi-messenger astronomy.
Moving on to Part 2. What exactly is a boson?
To actually catch our cosmic suspect, we first need to understand what the heck it's made of, which means zooming way down to the microscopic rules of quantum mechanics. All fundamental building blocks of matter fall into two camps: fermions and bosons. The stuff making up your body, the planets, normal stars like electrons, protons, neutrons, those are fermions. They strictly obey the Pauli exclusion principle. Basically, they violently resist occupying the same quantum state. It's that exact degeneracy pressure that keeps a neutron star or a white dwarf from just collapsing in on itself. But bosons, things like photons or the Higgs boson, they play by completely different rules. They have absolutely no problem crowding into the exact same quantum state, especially when they're supercooled, forming what we call a Bose-Einstein condensate.
Think about it like this. It's a great analogy. Fermions are kind of like people on a packed subway car during rush hour. Everyone needs their own personal space, and they're going to push back if you get too close. Bosons, though, are like a perfectly synchronized choir. When the conditions are just right, countless bosons can actually lose their individual identities and act together as one single, macroscopic quantum entity. So a boson star isn't some big ball of atoms burning gas. It's literally a giant, coherent, self-gravitating quantum wave.
Part 3. Define gravitational collapse.
So this brings up a pretty glaring question, right? If these things aren't generating outward pressure through nuclear fusion, or that fermion degeneracy pressure we just talked about, why don't they just collapse into a black hole under their own immense gravity? Well, the answer lies in one of the most famous rules of quantum mechanics, but playing out on a massive astrophysical scale: the Heisenberg uncertainty principle. When gravity tries to crush this giant bosonic wave function down, the position of the bosons becomes highly localized. But Heisenberg dictates that if you know exactly where a particle is, its momentum becomes wildly uncertain. That incredible momentum uncertainty essentially creates a powerful gradient pressure. The quantum field itself literally pushes back against gravitational collapse. It creates this beautifully delicate, stable equilibrium without needing a hard surface or an event horizon at all.
And when researchers simulate these interactions, we get to see this incredibly complex, fluid-like quantum math in action. Unlike normal stars that would just physically smash into each other, boson stars behave according to wave mechanics. Depending on their quantum phase, they might merge into a newly perturbed, oscillating star, or if we're talking about matter and antimatter equivalents colliding, they can dramatically annihilate each other.
Part 4. The dark matter connection.
So how does this tie into the bigger picture? Well, the physics of boson stars might actually hold the key to the dark matter that's holding our galaxy together. You're probably wondering how these things even form in the first place. Back in the chaotic early universe, massive clouds of these scalar fields could have existed. Through a mechanism called gravitational cooling, these clouds start collapsing under their own self-gravity. But
They can't actually form a star until they lose all that excess kinetic energy. And instead of radiating light or heat like a normal star, the system sheds this energy by ejecting scalar waves out into space. Eventually, the whole field just settles down into a bound, compact, and completely invisible object on the stable branch.
Now, the actual size of these stars, that depends entirely on the mass of the hypothetical particles they're made of. If dark matter is made up of ultralight bosons or axions, their wavelength is massive. And that means a single boson star wouldn't just be the size of our sun, it could literally be the size of an entire galactic dark matter halo. Just one star. On the flip side, heavier vector fields could form what we call protostars, which would be roughly the mass and size of standard stellar black holes.
Section 5. Cosmic Imposters, Black Hole Mimickers.
And this is the ultimate plot twist for us today. Because boson stars can perfectly match the mass and compactness of black holes, they might literally be hiding in plain sight. They are the ultimate cosmic imposters. Just think about the defining traits. Black holes have an event horizon and a central singularity, where physics just kind of breaks down. Neutron stars, they lack an event horizon, but they have a hard physical surface that matter crashes into. Boson stars, they have none of the above. No hard surface, no event horizon, and no central singularity. They are entirely regular, smooth configurations of space-time and energy. If matter falls into a boson star, it doesn't smash onto a surface, and it doesn't vanish behind a horizon. It just sort of collects toward the center.
Part 6. Hunting for phantom stars.
Okay, so if they're completely invisible and they perfectly mimic black holes, how on earth do we actually catch them? Well, because boson stars are transparent and lack that defining event horizon, light and matter behave very uniquely around them. Scientists are hunting for some highly specific observational signatures. For instance, in gravitational wave detectors like LIGO, the collision of two boson stars might leave these distinct echoes in the ringing of spacetime that would differentiate them from a standard black hole merger. Visually speaking, if a boson star is pulling in a disk of gas, the way the light bends around it would create broadened lensing rings. And because there's no horizon to swallow the light from the far side, at certain angles you might actually see a double shadow effect, shining right through the transparent star.
When we compare accretion flows between the two, it gets really interesting. If you look at a model of a standard rotating Kerr black hole versus a numerical model for a highly compact rotating boson star, you see distinct differences in the inner cavity. A stable, rotating boson star can actually suppress what's called magneto-rotational instability. That's essentially the turbulence that usually causes matter to fall inward. By suppressing that, it effectively stalls the accretion flow, producing a low-density, low-luminosity central cavity. Basically, an effective shadow, but without actually needing an event horizon to do it. It is subtle for sure, but next-generation observatories like the Event Horizon Telescope are actively looking for exactly these kinds of discrepancies to prove an object is a boson star rather than just a regular black hole.
Which leaves us with this final thought. A confirmed discovery of a macroscopic quantum object like a boson star wouldn't just solve the dark matter problem, it would fundamentally prove that quantum mechanics can dictate the structure of entire stellar-sized bodies in the cosmos. I mean, it bridges the microscopic and the galactic in one single swoop. So what do you think? If we finally catch one of these invisible imposters, is it going to completely rewrite the laws of physics as we know them, or is it simply going to prove that our universe is far stranger and honestly far more beautifully complex than we ever dared to imagine? Something to think about. Thanks for joining me on this explainer, and I'll catch you next time.